Hello everyone, welcome to the channel Statistica Hub. So in the previous video we are studying subspaces. Let's continue further. Subspaces. Okay. So today first we'll see about what are linear spans. Linear spans. We have studied about the spanning set previously. Let's see about the linear spans. What are these? So if I say that I have the vectors u1, u2 to um. Okay, if I have this set of vectors which belongs to the V vector space. Okay, this is belonging to the V vector space. Then any vector, any vector of the form of the form like linear combination of these vectors a1 u1 plus a2 u2 to am um. This is what? This is the linear combination of ui's vector. Okay, this is the linear combination of these ui's vector. Then the collection of all such linear combination, what? The collection of all such linear combinations is called linear spans of ui's, like depicting it like this, that span of ui equals to sigma ai ui for all ai belong to scalars say k is called linear span of ui's. This is what called linear span of ui's. We can also denote it like this, L of u. Okay, so what are linear spans? We have linear spans as if I have a set of vectors u1, u2 to um, which is belonging to the V, which is our vector space. Then any linear combination. What I mean to say about any linear combination is that all possible set of linear combinations, all possible set of linear combinations. Okay, is called as a span of ui. Okay, so when we take all set of linear combinations, then it is called span of these vectors ui's. This is our linear span. Okay, now I want to check that whether this linear span will form subspace or not. Okay, for checking subspace, what do we have to do? If I want to check that if a set of vector is forming subspace or not, then what will I do? If firstly I check whether the zero vector belonging to the set or not, whether if u comma v belonging to set V, then u plus v, sorry, w, that also belongs to w. This is closer under addition. Okay, and the third one is closed under multiplication, which is I have the vector u and the scalar multiple and the scalar k, which is the field of belonging to the field of scalars. Then I have uk, which also belong to w. Then these are the three properties which we have to check for the subspaces, and I have taught this earlier that the combination of these property we can check these property of 2 and 3 by a single condition, which is a comma b belongs to field of scalar and u comma v belongs to vector space. Then au plus bv, we can check them in a single condition like this. So if I want to check this subspace condition, that whether this linear span forms subspace or not, whether it will form subspace or not, let's check it. Okay, so first condition will be that this set of linear combination, which is a1 u1 plus a2 u2 to am um, where ai belonging to the field of scalars. Okay, so first we'll check for the zero, whether zero is belonging to this or not. So if I do it like 0 into u1, I'm putting it here 0, then what did I get? 0 then multiplying every vector by a 0 scalar, then I will get the resultant as 0. Then this is belonging to span of ui. So 0 vector is belonging to span of ui. Okay, second we'll check for that if I have v comma w which are belonging to span of ui, Okay, if I have these two which are belonging to this span of ui and alpha comma beta which are belonging to the field of scalars, then I have to check whether alpha v plus beta w belongs to span of ui or not. I have to check this. Okay, so let's see it. That I have alpha v plus beta w. Okay, then what is this alpha? What is the vector v? It is the linear combination. Let's represent it like a1 u1, a2 u2 to am um plus beta, which is w. That is another linear combination, which is b1 u1, b2 u2 to pm um. Okay, this is what? This is alpha a1 plus beta b1 u1 plus alpha b2 alpha a2 plus beta b2 of u2 plus dash dash alpha beta eta alpha am plus beta bm of um. Okay, so this is what? This is also a linear combination. Okay, and if I'm talking about the scalar field kv, let's check it this too. That is k a1 v1, k a1 u1 plus k a2 u2 plus k a m u m. Okay, so we can see from this here that like alpha v plus beta w. This is the resultant that we got from here. This also belonging to span of ui because it is also a linear combination. So what did we get from here? That span of ui is a subspace of vector space v. It is very important. It's very important. You're going to use it in many of the examples. Okay, so it is very important that span of ui is a subspace of vector space v. Okay, let's see it like this. That if I'm saying that, let's say I have a s set which is a subset of v. Okay, I have a set s which is a subset of v. Then if my set S is a phi, if my set S became phi, then what will be the span of S here is? The span of here S will become 0. The span of S will become 0 here. Okay, this is singleton. Singleton. Okay, now I have taken here the condition when S equals to phi. Now I am saying that S is a subset of V, and I have proved previously that span of S is a subspace of V that contains S. Okay, span of S is a subspace of V that contains S. And if I say that if W is a subspace of V, if W is another subspace of V that is also containing S, that contains S, then the span of S is subset of W. Then span of S is subset of W. What did I mean by this? I mean that here span of S is the smallest subspace. What? It is the smallest subspace of vector space V containing S. Containing S. What does it I mean here? In the sense, what is it? It means that every subspace of V containing S also contain span of S. Okay. Every subspace of V containing S also contain span of S. Okay, so this is actually a theorem. This is actually a very important theorem which said that let S be a subset of vector space V. Subset of vector space V, then first span of S is a subspace of V. Subspace of V that contains S, and the second is contains S. And what is the second condition? Second condition is that if W is a subspace of V, if W is another subspace of V that contains S, then span of S is subset of W. Span of S is subset of W. It means that span of S is the smallest subspace of V that is containing S. Okay? In the sense that every subspace of V containing S also contains span of S. Okay, so this is the smallest subspace of V, where if I'm let's say it can be also said like this, that any set of vectors, if I'm saying that any set of vectors which span V vector space and containing smallest possible number of vectors must be linearly independent. If I'm talking about this in the terms of linearly independency, then any set of vectors which span V vector space and containing smallest possible number of vectors. Number of vectors must be linearly independent. Okay, or it can also be conversely said as that a spanning set of vectors V which is linearly independent, okay, which is linearly independent, must be minimal spanning. Minimal spanning must be minimal spanning. Okay, in this, what we are saying, that any set of vectors which span V, the set of vectors which is spanning V. Okay, the set of vectors, let us say U, which is spanning V, containing smallest possible number of vectors must be linearly independent. The set of vectors which contains the smallest possible number of vectors, that has to be, and also spanning V. Okay, that is, I am saying that I have this set of vectors which is spans V, which spans V, and this set of vectors contain all smallest possible number of vectors. Okay, all possible that vectors that is containing S, that are the minimum vectors which can span V. Okay, the minimum possible number of vectors which can span V, then this set of vectors must be linearly independent. Okay, minimum set of vectors which span V, which span V, then this set of vectors must be linearly independent. Okay, and this is the converse theorem of this, that a spanning set of vector space V, a spanning set, I have a spanning set, like this is my spanning set, okay, which is linearly independent, this set is linearly independent, then it is what, it is the minimal spanning set, that this is the minimal spanning set, that this set is the minimum possible number of vectors which is required to span the vector space V. Okay, minimal spanning set. Okay, now let's see it like this, that we know that every non-empty set, that I have a non-empty set, every non-empty set is always contained in its linear span. Okay, every non-empty set will always be contained in its linear span. How? Let's see it like this, that if I say that S is subset of V, okay, S is subset of V, and let's say V is a vector which belongs to the set S. Okay, then how can I represent V as? V equals to 1 dot V which belonging to the linear span of S, and S is a subset of linear span of S. So every non-empty set is always contained in its linear span. Okay, Now there is another condition as this. Let's write it here point by point, that every non-empty set is always contained contained in its linear span. Okay, and if I say that I have two subsets of V, that is S and T, S and T, which are both the finite subset of V over the field K. Okay, if I have S and T, both are the subsets of V and over the field K, then if S is subset of T, then what does it mean? Then the linear span of S also the subset of linear span of T. Okay, and if each element of S is a linear combination of vectors of T, this can also be written as all. This can also be represented as that if each element of S is a linear combination of vectors of T, then L of S is subset of L of T. This is what we need for the linear span, that every can be written in their linear combination. So here we are saying that if each element of the set S can be written in the linear combinations of the vectors of T, then it is what? Then the linear span of S is the subset of linear span of T. Okay. Okay. Now let's see further. Let's see an example first. That I have the subspace of RQ. Determine. This is the question. That I have the two vectors alpha, which is 1, 2, 3, and beta, which is 3, 1, 0. Okay, what do we do here is we have to determine the subspaces of R cube spanned by these vectors. Okay, we have to determine subspace of R cube spanned by these vectors. First, we have to check that, let's say, if gamma equals to 2, 1, 3, whether this is in subspace or not. Okay, I want to check this, if whether this is in subspace or not. For this, let's say this L of alpha comma beta is a set of vectors. Okay, this is the solution part actually. If L alpha comma beta is set of vectors C alpha plus B D beta, which is a linear combination. Okay, that's what we do in the linear spans. Okay, where C comma D belongs to R. Then we'll just put the values of alpha and beta vectors, which is C of 1, 2, 3 plus D, which is 3, 1, 0, which is equals to C plus 3D, 2C plus D, comma 3C. Okay, now I want to check whether this gamma belongs to L alpha comma beta, whether this gamma belongs to the linear span or not. Okay, then it can be in the linear span if it can be written in their linear combination. If it can be written in their linear combination, like alpha equals to C alpha plus D beta, which is 2, 1, 3 equals to C plus 3D, 2C plus D, that's what we have solved here, comma 3C, which is equals to C plus 3D equals to 2, 2C plus D equals to 1, and 3C equals to 3. Okay, C equals to 1 and D equals to minus 1, and from this we got D equals to 1 by 3. And we can see that D has value 1 by 3 here and D has value minus 1 here. So it is what? It is an inconsistent equation. Inconsistent equation. So gamma does not belongs to L alpha comma beta. Okay, this is how we can check whether a vector belongs to this linear span or not. Let's see another example. If I have a set S which is alpha, beta, gamma, and another set T which is alpha, beta, alpha plus beta, um, let's say it is beta plus gamma. Okay, now I want to check the linear spans of these vectors. Okay, so here we can, I have two set S and T. Here we can see that each element of T is a linear combination of the vectors of S. Okay, that alpha is a linear alpha, beta, alpha plus beta, beta plus gamma. These all can be represented in the linear combination of the vectors of S. So from this we get that L of T is subset of L of S. Okay, got it? And another thing is the vectors of S. Each element of S can also be written in the linear combination of the elements of T. Like alpha equals to alpha plus 0 beta plus 0 alpha plus beta plus 0 beta plus gamma. If I have to write for beta, then it became 0 alpha plus beta plus 0 alpha plus beta plus 0 beta plus gamma. For gamma, I'll write it like 0 dot alpha plus minus 1 of beta plus 0 dot alpha plus beta plus beta plus gamma. So this can be written in their linear combination. Okay, so from this we get that L of S is subset of L of T. So what do we get? That L of T is subset of L of S. L of S is a subset of L of T. So L of S is equals to L of T. Okay. As so there is a one point to note here that L of S is the smallest subspace. What? L of S is the smallest subspace subspace containing containing set S containing set S, and it is actually the intersection of all subspaces of V that contains the set S. Okay, that's why it is called the smallest subspace that contains the set S. And the second point is that the linear spans of S is equals to the L of S. Okay, you got it. Let's see it, a very important theorem. There is a very important theorem which is that the subspaces of R square are zero. The lines though the lines though the origin and R square itself. Similarly, the subspaces of R cube are zero, which is the lines through the origin, the planes through origin, and R cube itself. Okay, let's see what does this mean. So for subspaces, as I have said, for subspaces, for checking subspaces, what we have to check? Firstly, we have to check whether 0 will belong to this or not, and the linear combination AU plus BV going to belonging to this W or not. Okay. So here we are saying that the subspaces of R square, the basic first requirement will be that the zero vector should belong to this W. Okay. The subspaces of R square are zero. The subspace of R square 0. The line that means the lines to the origin and the R square itself. Okay. So if I draw the lines to the origin, all the lines which are going through the origin must contain the zero vector, as these are passing to the origin. Okay, these lines, all the lines which are going through the origin, like this, these all contain the zero vector, and they all satisfy the linear combination of these vectors, that au plus b belongs to this w. Okay, so from this we get that the lines to the origin form the subspaces. What? The lines the origin form the subspaces. Okay, as they satisfy the condition of the zero, condition of the subspaces which is zero, as they are passing from the origin, they are satisfying the first condition, and they are also satisfying the addition property and the closure under addition and the closure under multiplication property. Okay, now if I talk and the R square itself, and you know that the R square is actually a vector space, and every vector space is a subspace over itself, so it also forms a subspace. Okay, and similarly for the R cube vector, the lines to the origin, all the lines to the origin contains the zero vector and satisfies the property of addition and the multiplication, closure under addition and closure under multiplication too. So it also forms a subspace. And if I talk about the planes, then how does planes be depicted as? These are the planes, something like this. And all the planes which passes to the origin, let's say like this, all the planes which are passing to the origin are the does form the subspaces. Like they satisfy the first one, they satisfy all the requirements of the subspaces which is passing to the origin, so they contain the zero vector, and they satisfy the properties of closure under addition and the closure under multiplication. So from this we get that the subspaces of R square are zero, the lines to the origin and the R square itself, and the subspaces of R cube are zero, that's the lines to the origin and the planes to the origin and R cube itself. Okay, so here we are talking about the lines which are passing to the origin and the planes which are passing to the origin. So, and we have seen that there are some lines, there are some planes which does not pass to the origin. What about them? Let's see those. Okay. Uh, let's say for understanding that concept, first we'll need to know a term which is like this. If I say this is actually a definition which we need to know before understanding that the sum of any two subsets, the sum of any two subsets A and B of a vector space V is, how can we write it? The sum of two subspaces, the two subsets A plus B equals to X plus Y, where X belongs to A and Y belongs to B. Okay, now if I say that X is our singleton, that if A singleton, sorry, if A is singleton, that means if A has element X, then the sum of these two subsets can be represented as X plus B, X plus B, which is said to be X plus B is X plus B is a translate of B. If this is the condition applied here is that if a subset is singleton, that is X, if a subset X if a subset A is singleton, which is X, then X plus B, but then we can represent the sum of them is as X plus B. Then we said that this is a translate of B. Okay, now we are going to use it further like this, that okay, so as I'm talking about um, the lines which are not passing to the origin, the planes which are not passing to the origin. So in geometry we also have interest in the lines and planes not necessarily passing to the origin. The lines which does not pass the origin, the planes which does not passes to the origin are called flats. What are these called? These are called flats. Okay. Now if I define it like this, that a set A, okay, a set A which is a subset of V is said to be a flat, is said to be a flat, or you can say that a fine set, a fine set if, when it can be said flat or a fine set if A equals to phi, or A is a translate of a subspace. So it can be said as flat if A equals to phi, or A is a translate of a subspace. What does it mean? That is A equals to x plus s for some subspace S of V. For some subspace S of V. Then can we say that A is a flat or affine set? Okay. Then if I'll talk about the affine combinations, what are the affine combinations? Let's say I have the affine set of A. I have the elements of A as x1 to xk. Okay. Then the affine combinations of these is a linear combination alpha 1 x1 to alpha 2 x2 to alpha k xk, where the sum of alpha 1, alpha 2 to alpha k must be equals to 1. This is the condition applied for the affine combination, for the set of affine combination to be the affine combination. Okay, so this is called the affine combination. So if I say that A, which is a subset of V, is a flat, what does it mean? If a subset of A is, if A is a subset of V vector space is a flat, it means that either A is equals to pi, and either A is a translator vector space V. Okay, if A is a flat, so A, which is subset of V, is a flat if A is closed under, if A is closed under affine combination. What? Affine combination. And we have defined the affine combination. Let's say as here we can say that x1 to xk we have the vector which belonging to the set A, and alpha 1 to alpha k we have the scalars which belonging to the field of scalars, and the affine condition which is that alpha 1 alpha 2 to alpha k has to be the 1, the sum of these alpha k has to be the 1. Then this is the affine combination. A is the affine combination which is alpha 1 x1 to alpha k xk belongs to A. Then we can say that A is a flat. Okay. So this is just the basic. Maybe you'll need this in some of the topics. It is not like that much important, but you are going to need it further in your further studies. Okay. Now in the previous video, we have studied about the homogeneous space. Homogeneous space. Okay. Sorry. Actually, the solution space of the homogeneous system. Okay. We have studied about the solution space of the homogeneous system. That the solution space of a homogeneous system forms a subspace. Okay. Now, in this topic, we are going to see the row space and column space of a matrix. What? Row space and column space of a matrix. Let's say I have a matrix A of M cross N. Okay, I have this matrix over, let's say R over K, whatever the field. Okay, I have this matrix. Then the rows of these matrix are R1, R2, 2, Rm. These are the corresponding rows, and C1, C2 to Cn. These are the corresponding columns of this matrix. Okay. If I take out the first row, R1, then what does it say? That A1, the elements of the R1 are like A1, A12 to A1n, which belongs to R's power n. I'm taking this as on the real field, okay, which belongs to the R's power n. So from these are what called? These are the row vectors. Row vectors. These are R1, R2, R3, Rm. These are the row vectors, and these are C1, C2 to Cm. These are the column vectors. Okay. And R1, the row vector, can be represented as the corresponding elements of these vectors which belonging to the field R's power n. This is the row vector. Now, if I say that that from these row vectors, first we'll make a set of these row vectors. Let's say I have a set S, which is the set of these vectors, row vectors R1, R2 to Rn. I have formed the set of these row vectors. Then how we can define the row space of A? So row space of A is the span of all linear combinations of Ri's. Ri's means the row vectors. Span of all linear combinations of the Ri's, which is span of R1, R2 to Rm, which is span of the set S. Okay. What does this is what I mean by here is. Okay, so this is my span of RIs. Span of RIs. Okay, so from this we what we get. So why are we writing it like this? We are writing it like this as what is the span? What is the span? Span is writing in the all possible linear combinations. Okay, so I am doing the same thing here, that I am spanning all the rows. Span of this is what all linear combinations of RIs are i's, all linear combinations of the row vectors. So what is here? This row space of A, this is the row space of A, which is defined as span of Ri's, all linear combinations of the row vectors. Okay. So now I want to check whether this row space of the matrix A will form subspace or not. So for checking this, let's see, I am checking that whether this row space of A will form subspace or not. Okay, subspace of R's power n. Okay, for checking subspace, first we'll do what we'll do first. We'll check for the zero vector, which is if I say, write it like check for this, that 0 R1 plus 0 R2, the linear combination of these vectors, plus 0 Rm. This will give us the resultant will be 0, and this belonging to the row space of A. Okay, as in the matrix there is a row which there can be a row which is the zero vector. Okay, and now let's check for the another one, which is alpha comma beta belonging to the row R, and they belonging to the real number actually. And I have two rows which is R and R dash, which belonging to the row space of A. And the linear combination of these, which is R alpha R plus beta R dash, would be somewhat like sigma of alpha AI plus beta of bi of ri. Okay, which also belonging to the row space of A. So from this we get it is satisfying the properties of subspace, that the row space of A forms the subspace, is a subspace of R's power n. Similarly, if I'm talking about the column space, it follows. It goes similarly, like column space of uh, column space of A also forms a subspace like this. Okay, so column space of A is also a subspace of R's power m. Here, one point to note here is that I have a matrix of A m cross n. I have a matrix of A m cross n. Then the row space of A is a subspace of R's power n. R's power n. And the column space of A is a subspace of R's power n. Okay. This is to note here is that of which power I am taking. If I have a matrix of A m cross n. Okay. Because why are this, you can, I think you can get it, because if I'm taking the row space, let's say I have a row of R, I'm taking the row R1, which is A11 to A1n, which is what this belongs to the R's power n. R's power n. And if I'm taking the column vector, which is B1 B2 to B1m, this belongs to the R's power n of the that I have the matrix as m cross n now. Okay, that's why it has R's power n and it has R's power m. Okay, so let's say that we can see that I have the matrix m cross n. Then you can easily see that the column space of A transpose. A transpose matrix, that the column space of A transpose A matrix is equals to the row space of A. Okay, and the column space of A is equals to the row space of A transpose. And I have the matrix A M cross N, and this is can be, this is the matrix A, and this is the matrix A transpose. Okay, I think you got it. So this is the row space and the column space which forms the subspaces on their corresponding matrices. Okay, let's see it like this too. That we have studied the concept of equivalent matrices. Okay, when I have two matrices A and B two matrices, these are equivalent. A is equivalent to B if one can be obtained by other using the E-row transform E-row operations. Okay, if one can be obtained by other by E-row operations. And what are these E-row operations? E-row operations, let's say this is Ri to Rj, interchanging. Second one is scalar multiple, which is if I multiply Ri, the row Ri by Kri. And third one is like adding Ri to Ri plus Krj. So these are the corresponding E-row operations. Okay. Now, why am I including this topic here? I am saying that after I have the matrix A, and after applying E-row operation, okay, E-row operation, what did I get? I get the another matrix which is M. Okay. So A is equivalent to M. A is equivalent to M. Got it? As each row of M is a row of A. Each row of M is a row of A, or a linear combination of rows of A. Okay. So what can we write here is that row space of M is the subset of row space of A. Okay. How? Because each row of M, we are applying here the E-row operations on M. That is a linear combinations of the rows of A. Okay, so the row space of M is a subset of row space of A. Now, if I say that I am applying to A the row operations, then I got the matrix M. And from this I get the row space of M is subset of row space of A. And if I apply the inverse operation, what did I get? Then I am applying the on the matrix M the inverse operation to get the matrix A. Okay, from this we'll get that the row space of A is subset of row space of M. Okay, so from these two conditions I got that the row space of A is equals to the row space of M. Okay, so from this we got that the row equivalent matrices have the same row space. What? That the row equivalent matrices have the same row space. Or you can say that I have the two matrices A and B which are in the row reduced echelon form. Row reduced echelon form. Why am I saying this? Why am I teaching this concept now? Because to finding the row space, okay, we cannot find the row space of any matrix just like simply. We have to reduce it to the echelon form. We are taking here the concept of echelon form, reducing it that here. Okay, so let's say if I'm saying that I have the matrices A and B which are in their row reduced echelon form. Row reduced echelon form. Then A and B have the same row space. A and B, these A and B have the same row spaces, same row space if they have same non-zero rows. What? If they have same non-zero rows. Let's see it by an example. Let's say I have the vector u1 which is 1 2 minus 1 3, and another vector u2 which is 2 4 1 minus 2, u3 which is 3 6 3 minus 7, and this U spans the UIs, span on the UIs. And another set of vectors which is W1, 1, 2, minus 4, 11, and W2 which is 2, 4, minus 5, 14, and this W spans the WIs. Now I want to check whether the row space of these are equal or not. Okay, so first we'll give for check, not just talk about the row space. First, let's say I want to check whether the spanning of these are equal. Okay, whether U equals to W or not. Okay, so in our first method, which we have earlier, we have to show that each UI is a linear combination of W1 and W2, and each WI is a linear combination of UIs. That is, we have to show 6 system of linear equations are consistent, and that is a very long process and a very long calculation. So from excluding these calculations, what we'll do, we'll transform these vectors into the matrix form. Okay, let's say I give this matrix a name A. This is my matrix A, and we'll transform these vectors in a matrix form like this: 1, 2, minus 1, 3, 2, 4, 1, minus 2, 3, 6, 3, minus 7. Now I will transform this matrix to the echelon form. Okay, now let's deduce it. If I apply, um, let's say I'm applying in R2, R2 minus 2R1, and in R3, which is R3 minus 3R1. If I do some mistake, just tell me. 1, 2, minus 1, 3. Just solve it carefully. 0, 0, 3, minus 8, and it will 0, 0, 6, minus 16. Okay, I got this. Okay, now let's transform, let's do another operation, which is r3 r3 minus 2r2. Okay, it will give us 1, 2, minus 1, 3, 0, 0, 3, minus 8, and 0, 0, 0, 0. And let's transform it more. I will reduce it, divide row 2 by 3. Then it will become 0, 0, 1, minus 8 by 3, 0, 0, 0, 0. These are my 1. I got this and this. This is my pivot element. These are called pivot element. We'll study this matrix concept earlier further in the upcoming lectures. So okay, these are pivot element. Then I got this matrix from reducing the matrix A. Now let's deduce another matrix, which is B. We have to erase it. Let's say I'll transform the vectors of W in the matrix B. Okay, and then we'll try to reduce this into the echelon form, in the row echelon form. Okay, this is our matrix B, which is 1, 2, 2, 4, minus 4, minus 5, 11, 14. Okay, now reduce it. We'll reduce it to 1, 2, minus 4, 11 on row 2, like R2 minus 2 R1, which is 0, 0, 1, and it is minus 8 by 3. Okay, and if I reduce it, it will become 1, 2. Now, what we'll do, we'll reduce it to the row reduced echelon form and row canonical form. Then we'll have to, this should be the only element which has the pivot element is the only one which is the element 1, and other than we have to do otherwise 0. Okay, similarly for goes here, we also have to reduce it in this column. The pivot element only the one which contain 1, and other element should be 0. It should be 0 and it should be 0 too. So we have to reduce it to the 0. Reduce it to 0. We'll apply the operation here, which is 1, which became 1, 2, we'll just add these two. 1, 2, 0, 1 by 3, 0, 0, 1, minus 8 by 3, 0, 0, 0, 0. This is our pivot column, this is our pivot column. And we'll do same for here. We'll reduce it to the row canonical form. Row canonical form, where what is row canonical form? Row canonical form is this, where the only the pivot element is the element which is non-zero. Otherwise, all the elements are zero. So we have to reduce minus 4 to 0. We'll do here 1 2 0 by applying the operation 1 2 0, and it will become 1 by 3, 0 0 1, and minus 8 by 3. Okay, I got these two pivot elements here. So we can see that I got the vectors as non-zero rows of matrices in row canonical form. These two rows are identical. I have 1 2 0 1 by 3, and I have 1 2 0 1 by 3 here too. And these two rows, two non-zero rows are actually equivalent, are identical. So from this I got that the row space of A is equals to the row space of B. So U equals to W. I got U equals to W. Okay. Now, if I say that I have a matrix A which has M cross N. Okay, this is the matrix on M cross N, and I have another matrix of P which is M cross N. Then if P is non-singular, what if P is non-singular? Then A and A and PA will have same row space. Same row space. Okay. So here we are just for the example we have taken the concept of matrices. We'll understand the concept of matrices further. Row operation, transformation, column operation, or canonical forms or reduced echelon forms. We'll study these in detail in the further lectures. Okay, so this is the concept of the subspaces. Whether you have studied the concept of row space, column space, and um, in the homogeneous system, we have studied the solution space too. Okay. Thank you. Let's meet in, in the another lecture.